Swayam Prabha. Digital India. Educated India.
So in the previous classes, we were looking at Brownian motion, and Brownian motion can be described through a differential equation that describes the motion. And so this is something very different in the sense that the dynamical equation has some random components, and that kind of encodes the irregular motion of the Brownian particle. So even though this Langevin equation was developed for explaining Brownian motion or irregular motion of Brownian particles, subsequent development led to far more applications, okay, wherever there was irregularity in motion, and the framework, Langevin framework, is used. So I am going to build on that and show some other scenarios where we can apply Langevin dynamics to solve other kinds of problems also. Okay. So that is the context of this lecture. So we note that the Langevin equation has this sort of formula, okay, and we say that this characterizes the free Brownian particle. I say free Brownian particle is because there is no other interactions with this particle, okay, there is no wall confining it, there is no external field affecting it, or there is no other neighboring particle affecting its motion. So we are thinking about a very dilute condition where we are looking at only one single particle and its dynamics, and that is governed by this equation. So let us say if I have a population of Brownian particle, and these particles will also start interacting. So then you can actually add extra interaction forces to this, okay, or let us say this Brownian particle is subjected to a gravitational force, then we are talking about sedimentation problem. We can also apply this. So it depends what sort of force that is acting on it. The kind of force I am talking about are called conservative forces. So conservative forces are those which can be related to some sort of a potential function, and when you take the derivative of the potential you get a force. Those are classified as conservative forces, those are deterministic forces, okay, like I said, gravitational force, electrostatics, magnetic interactions and so on, or interparticle interactions through van der Waals and so on. But if you think that a particle is subjected to some sort of a random external force, you can also add to that, okay. So depending upon the physics of the problem, you can always add additional forces here, okay. So you can say, for example, so this is for a free Brownian particle, and if you want to say a particle under a external field, you would have some additional force, and you have to prescribe what this force means. You know, is it a gravitational force? Is it a any other kind of body force? You know, that's where as a modeler you will have to describe what is the nature of this. This can be a deterministic force, it can be a random force if it is coming from some other randomness. Already we have taken care of the randomness associated with the molecular collisions. If you think that this particle is subjected to some other kinds of random force, you can encode it, okay. So here we are leaving it open, okay. Then no longer we call this as a free Brownian particle, we say this is a Brownian particle under an influence of an external field or the neighboring particle or any other additional forces, okay. So you can see some sort of generalization we are already making. We are starting from a free Brownian particle developed to describe the irregular motion of Brownian particle, then we can customize to a new condition depending upon the environment with which this particle is actually executing its motion, okay. So now many times when we try to add anything here, analytical result may not be always possible, okay. Again, it depends on what sort of force you are going to have, okay. So here we show that you can derive an analytical expression for the mean position, mean square position, mean velocity, mean square velocity, all that we showed in the last class, Okay, as far as a free Brownian particle is concerned, you can analytically solve this equation. But the moment you bring in additional effects, then you have very few cases where you can analytically solve. In many times, we would actually end up solving this numerically. Okay, so then we have to talk about how we are going to solve this numerically. I'm going to only focus on the numerical aspect of this side, because the other part you know how to solve a regular ODE using Euler's method, Runge-Kutta method, okay, any other numerical technique. Okay, discretize a time, initialize, and then you have a different degrees of accuracy to do this. But how are we going to handle this particular random force? Okay, so I'm going to focus on that particular issue, and our analysis will be first starting from simulating a Brownian particle numerically, and therefore we can also compare the results because we know analytical results for this. So that will be like benchmarking. Once we know that, then we can go to a more general case for which maybe analytical results not possible, but adopt a numerical approach. Okay, and gives us so much power to you to simulate any sort of condition under which a Brownian particle is executing its motion. Okay, so therefore what we want to say is that we will come back to this later. We will keep this free Brownian particle under consideration, and let us remind ourselves what is the characteristic of this force is. Okay, so we said that the mean of this force is 0, and the autocorrelation function for this was given as m square gamma delta of t minus t prime. Okay, so these are the conditions about the random force acting on the Brownian particle. And we know that this is a delta function. What we are saying is this autocorrelation function is a delta like function. Okay, and it is non-zero only when t is equal to t prime. Okay, so if I plot this autocorrelation function as a function of time delay, so this is a time delay, I am looking at the random force at two different times separated by a interval of t minus delta t, and that would actually peak at a 0 as a delta function. That is what this means. Okay, physically what it means is that the random force acting on this particle is time uncorrelated. The collision happening at the force acting on particle time t and the force acting at another time t, these are actually uncorrelated. Okay, so the mathematical statement of this is what we have shown in terms of this delta function. This number is non-zero only when we are talking about instantaneous collisions. Two collisions separated by some time is actually uncorrelated, that is why it vanishes immediately. Okay, so the mathematical statement here basically means that we are only specifying the variance, okay, at time t, and it does not correlate with its collision before or after. Okay, it's instantaneous. Now how do we encode this here? Okay, so what we can think of this is this having a 0 mean and finite variance, and we also can show that this L of t is nothing but a normal Gaussian random variable. Okay, so L of t is a Gaussian distributed with mean 0 and variance of this m gamma square. Also remember that in the previous discussion we also qualified what this m gamma square is. Okay, anyone can recall what is m square gamma? We showed that this gamma here is actually related to the friction coefficient and temperature via this. Okay, so it kind of tells you the magnitude of the mean square force, random force. Okay, So now what we can do is then we can say that at any time t, the random force L can be expressed as some mu plus sigma some eta of t, where this eta of t is a normal random variate with 0 mean and unit variance. So as far as this free Brownian particle is concerned, we are saying that this random force is Gaussian distributed with a mean value of 0 and a variance of sigma square. Sigma square is nothing but m square gamma, and m square gamma is related to 2 gamma kbt. We are saying this. Now I can rewrite this random force which is Gaussian distributed through a normal random variate with 0 mean and unit variance via this transformation. Okay. So in probability course you must have studied this, that by using a normal random variate with 0 mean and 1 unit variance, you can write another Gaussian distributed with another mean and another standard deviation through this transformation. Okay. So this value will be between 0 to, will be from minus infinity to plus infinity, okay, it's normally distributed with a variance of 1 and mean is 0. This is something we can generate based on the numerical algorithm we discussed before. Okay, the Box-Miller algorithm, the polar method that we talked about. So whenever you call a function, you should get a number that would have 0 mean and variance being 1. Once you get that and you operate by this, okay, then you would have created an instantaneous random force needed for this particular time. Okay. So substituting here, L of t is nothing but, anyway mu is 0 even for this, and it basically becomes sigma is 2 gamma kbt square root and eta of t. So what we are saying is, if you want to numerically simulate this trajectory or this equation, at any time you are going to discretize your time. At each of this time you are going to calculate all these parts, and whenever you want to calculate this L of t, you would actually generate a random variable which is eta of t, normal random variate, and then multiply by this prefactor, then you would have generated an instantaneous force. Remember, this number can be both negative and positive. Okay, and then if you would generate a large number of such a random variable, and then if you do sum of that, that would actually add up to 0. The mean will be 0, but the mean square and variance will survive. So therefore we are saying that there is a way that we can numerically calculate the random force needed at any given point of time, and that will be used in this equation. The rest of the numerical discretization one can do. Okay, you have a question? M square gamma, yeah. Oh, here, okay, yeah, you're right, yeah, sorry, yeah. So this should be M square gamma, yes. Yeah, thanks for pointing this out. Yeah. So all this analysis we have done for one dimension, okay, but in reality this particle can move in a 3-dimensional thing. Then what we need to do is just write this equation and these terms in a 3-dimensional vectorial form. Okay, so that also I'm going to do it now, so that it is quite general from here. Okay, this is done for a single 1 dimension. We are going to do for 3 dimensions, and okay, maybe I can use a color, different color. So this V becomes a 3-dimensional velocity having components x, y, z components. So here also we will have this, and this also will become a 3-dimensional quantity, 3-component quantity. And so what we are saying is we can actually do two things. We can say 3D, and also you have, let's say, n free Brownian particles. So then we are talking about collection of n number of Brownian particle undergoing free Brownian motion in 3 dimensions. Then this equation will become simply, I have to put an index I here, so that for each particle I 1 to n, I can use this equation. Okay, so we are solving the Langevin equation for each particle. Okay, so this is a mass of the particle, this is a velocity, 3-dimensional velocity of the ith particle, this is the drag force acting on the ith particle, and this is a random force acting on the ith particle. Okay, and then this I can go from 1 to n. Okay, so we are simulating n number of free Brownian particle by this. So in this case, what we can do is by this transformation, I can rewrite this. So I have replaced this random force through this substitution, and also note that this normal random variate also is now a vector. This also will have 3 components now for every particle I. So when I look at 1-dimensional normal random variate, I can simply say it has a mean 0 and variance of 1, but when we try to do this, this also has to be transformed here. So here, this expression is a little bit complicated, let me walk you through. So what we are saying is that for the mean, this is 0 for all the components, x, y, z component, for ith particle, this is clear. So here we are trying to say about the variance or autocorrelation function between particle I and particle j, and for each of the components. So here this would have 3 components and this would have 3 components, but this is transformed. So therefore this product would actually have a 3 by 3 matrix of all components. Okay, so if I have to expand this, you would see you would have gamma ix at t and gamma jx at t prime. Okay, and then you will have similarly 9 such components. Now what we are saying is the only terms in this, all of this 9 components, the only terms that would actually be surviving are those where the times are the equal and I and j should be equal. So this is a Kronecker delta. What it means is the random force acting on ith particle and j particle are actually uncorrelated. They are only correlated if I and j are same. So this will become 1 only when I and j are equal. And this is a unity matrix 1 0 0 1 0 0 0 1 0 1 0 0 1, and this one will take care of the instantaneous of the collisions. So therefore the outcome of this is you would have a matrix like this only if I and j are equal and t is t prime. Only then these values are taken. When this is not when this condition is not met, then they are all 0. Okay, so this is a way to write a 3-dimensional or the vectorial form of the correlation function. Okay. In other words, what it means is, when you try to use this equation, what you're going to do is, for every particle I, you're going to calculate 3 independent normal random variate, and you're going to use it here. Okay, so that's what the meaning of this this statement here means. So from here, we can also think of a special condition that if you look at this equation, so you have this inertial term. Okay, you can also think about some time scale where this inertial term will actually vanish, and then you can think about what is called this over-damped limit. Okay, so to see that, we actually divide this equation by gamma. I have m by gamma dv by dt. Again, in this context, I am going back to this case of one-dimensional free Brownian particle, and when I write this equation in this form, I think there should be a gamma here also, right? So now if you look at this terminology, this term actually has a unit of time, okay, and this we define as a inertial time. This is inertial time. So for time t less than tau I, inertial effects would be seen. Inertial effects will dominate. For time t much larger than tau I, only diffusive effects dominate. So what do I mean by that is, suppose if I take the original equation, okay, and I solve, and then I calculate the mean square displacement analytically or numerically, and then if I plot mean square displacement versus time, you will see 2 kinds of scaling behavior. At a short time scale, you will see the mean square displacement will be proportional to t square, okay, and this is what we call it as a ballistic or inertial regime. But if you look at long time effect, you see this mean square displacement has a different scaling, where the mean square displacement is proportional to t, not t square, and this we call it as a diffusive or over damped limit. Okay, why we call over damped limit? Because this is related to again nonlinearity and overshoot, how we analyze a second order differential equation. So this is a second order differential equation with respect to x. Okay, so in case where this inertia dies out, you will see a damped response, and that's why we call it as an over damped limit. So you will see this kind of a behavior. This is something you will actually can show if you solve this analytically. You can see the expression in Chandrasekhar's paper. He gives this x square as a function of t as the following. So, I think okay, maybe I can replace beta into 1 by tau. Yeah. This is the analytical result for the mean square displacement when you analytically solve this full equation. Okay, and if you plot this function, you see that you have a sort of a ballistic regime, and then subsequently it goes to a diffusive regime. So now many times what happens is that this because the Brownian particle size we are talking about is very small, the mass is very small, and gamma is quite quite high because it's a viscous liquid. This time scale is very short. With regard to our observation time scale, this initial time scale is very small. We generally do not resolve dynamics on such a short time scales, even though I have shown like they extend over a significant period of time, but actually this scaling happens to be a very short time scale, and then what you actually see in an observation time scale is this diffusive behavior. Then if our interest is only in looking at diffusive behavior of a Brownian particle, what we can do is we can actually ignore this term. Okay, we can ignore this inertial term, and then we look at only response in the larger time limit where only the diffusive behavior will actually exhibit. Okay, so then what we say, we put this equal to 0. And this we call as the overdamped Langevin equation. So from here we can write that V should be equal to 2 kBt by gamma eta of t. So this is going to tell you how the position of a Brownian particle will behave under overdamped limit. Okay, and if you want, you can replace this into dx by dt, and then you can integrate this for x, and thereby you can create the trajectory of a Brownian particle under overdamped limit. If you create the trajectory numerically, and then if you calculate the mean square displacement from there, what you would see is only this part. This equation cannot give this response. Okay, so this equation, if you solve, it will show that mean square displacement as a function of time in the log scale will have a slope of 1. This overdamped Langevin dynamics is also noted as a Brownian dynamics. Okay, in the literature, people say that this simulation is Langevin dynamics or Brownian dynamics. When you say Langevin dynamics, you are solving the full equation with inertial effects. When you solve through Brownian dynamics or Brownian motion, you are looking at only the diffusive aspect without regarding the inertial aspects. Sorry? Because that in the time scale at which what happens is the inertia is actually died out, and there is a viscous damping effect of the liquid that will dominate. Okay, so if you want to look at from a more molecular point of view, when a particle gets a kick at any given time, there is a net force acting on this particle. So the particle will respond. Initial response will be inertial, but then over a period of time, the solvent will recognize this motion. As the particle picks up speed, the drag will try to resist it, it will try to dampen it. So in the long term effect, it's actually the damping effect. So the over damped basically means the damping actually is overwhelming, and then the inertia will actually die out. Okay, so that basically means the particles are not accelerating anymore. That's what it means. Okay, there's no acceleration. Particles are actually cruising at a constant speed kind of thing. Then you are solving, in that case, how the particle will move. Suppose if I didn't have this term, you would predict a kind of a linear trajectory. But this one gives you a plus minus value. A particle can move back and forth. You can see how we did the random walk problem in the first case. We had a very similar kind of an expression. The particle can go forward or backward with some constant value, and that's exactly where this is coming from. So the one-dimensional random walk we did before is actually a simplified version of this equation. So in the notes I am going to share, I have given a tabular form summarizing all the results: one-dimensional random walk, Langevin dynamics, under-damped, over-damped Langevin dynamics, Chandrasekhar's full derivation of the problem, and then the key results and plots. Okay, that's something for you to go through. I did not mention here, but you can appreciate that even though this we wrote for one-dimensional free particle, if you want to do for n particle, you can apply this equation for all the particle. And if you want to do for three-dimensional case, this x will be a vector, x1, x2, x3, or three component of the position. Similarly, the random variable will also have a three independent normal random variate. You can extrapolate. Okay, so this equation is applicable for 3D n particle system also. And then if you want to add extra terms, if you have any drift velocity, you can also add. So I'm going to give you one example. I mean, I'm going to talk about several other examples, but in view of time, I'm going to talk about one particular example, and this is a very active research field in which this Brownian dynamics or Langevin dynamics is very much used. So these are called self-propelling particles, or active particles. Have you heard of these terminologies before? Active? Huh? Activated charcoal. Okay, I don't know what that means. Oh, okay, that has a different perspective. Activated charcoal is to have more surface area and related to adsorption and reaction. This active means no, not that. Anyone else? Self-assembly. What do you understand by self-propelling? I mean, literally what it means. It means that something can actually propel by itself. Do you know any things that does this? Huh? Tadpoles, yeah. What about us? Don't we self-propel as we move? Any locomotive object, okay, is self-propelling. So, but here this subject doesn't concern us because we are too big. We don't execute Brownian motion. Okay, we are inertial driven. But if you look at the smaller objects like microorganisms, bacteria, cilia, and so many other set of microorganisms, what originally even Brown's observations mentioned, those are in that right length scale where the Brownian motion is dominant. Yet they can also have a biological mechanism by which they can swim, they can project their motion, they can actually propel themselves through some sort of biological mechanisms. So very simple example is E. coli bacterium. Okay, if you have seen E. coli bacterium, it is a rod-like bacteria. It has about a micron length, and it has some flagella, and it manipulates the flagella's orientation such a way that it can produce a torque, it can produce a translational rotational motion by which it can actually go. Why bacteria wants to move? Because it wants to search for food. It tries to sense something and then keeps moving. So if you go to YouTube and if you see E. coli dynamics, you will see a lot of pictures and movies are available. Now this Langevin dynamics actually can be used to understand how collectively bacteriums will move. When the bacterium moves and become dense in local location, they form what is called biofilm. So it's very important to know how biofilms form, under what conditions. Sometimes you want to make a biofilm, sometimes you want to avoid the formation of biofilm. Okay. So there is a whole lot of literature on understanding the collective dynamics or self-assembly, as he said, of particles that has this inherent self-propulsive mechanism, yet they are also Brownian. Okay. So then what we can do is we can actually think about writing a set of Langevin equation under wow damped limit to describe the dynamics. Yeah. Yeah, drug delivery is one application, yes. You can have a particle and then propel it through some sort of a mechanism, and they will be subjected to Brownian motion. So motion will be a little bit chaotic, but then there will be a drift towards the target. Okay. So for simplicity, we will think about a circle in 2 dimension, and then we will associate a direction to this, and this direction is a random variable. Okay. This particle translates due to Brownian motion. The particle can also change the orientation, okay, because there is an internal mechanism for it to, in fact, there is a nice book called Physics of Foraging. This book actually talks about the trajectories of many kinds of organisms and how they search for food. Okay. Brownian is very, very common, but there are some special organisms, they will do between Brownian and inertial, ballistic. They will do execute a Brownian motion locally, and after some time they go in a targeted direction up to certain distance, and then they explore locally. Okay. So there are several such combinations of dynamics that makes an organism search for its food. Okay. So highly appreciate. I will give the reference of the book in my notes. You can take a look at it. It's a very interesting book. They give a lot of nice scaling law for foraging of many organisms. So coming back to this problem, imagine this is more like a bacterium. Okay, but here for simplicity we have taken as a circular disc. Okay, and has a radius of r, and there is an orientation. Then this orientation vector also going to change. Okay, so then we will say that this particle is actually propelling in this direction with certain velocity Vp. This particle is able to generate enough thrust within, so that in this chosen direction the particle can have a constant velocity. Okay. At another time the particle may move somewhere else and it may change the orientation. In that direction it will go. Okay. So that's what it's called, an active particle or self-propelling particle. So what you have to say, this is a Brownian particle. Yeah. That's what we are going to do. I am going to write a separate Langevin equation for the orientation and for the translation, right? That's exactly what I am going to do. Yes. So for example, I can write the exposition as per that is 2D. By the way, Kp by gamma is nothing but a diffusion coefficient. So that's why I have written 2D eta x. This would actually mimic the Brownian motion, but like I said, this particle is also propelling in a given direction with a velocity v. Okay. So then there is an additional component here. The additional velocity is Vp some cos theta. Okay. It is resolved in the x coordinate as Vp cos theta. Similarly, the y coordinate of this right. So these equations tell you how x and y will evolve in time, but the theta here is the one that tells you about this orientation with respect to, let's say, x axis here, and this also is a random variable. Theta is also a random variable. So we have another equation, d theta by dt is given by another random variable here. We say 2 dr eta t. This random variable is also Gaussian distributed, okay, and has a mean of 0 and variance of 1, and the prefactor governed by the rotational diffusivity of the particle. It's a free diffusion. Okay, In fact, we wrote some papers where we even added an angular velocity to this. Sometimes the particle can also rotate with a particular angular velocity. You can add that also. But right now in this model, we have a free rotation. The particles are undergoing some sort of a free diffusion in the rotational direction. So you have a set of 3 differential equation, okay, and if you solve this, you can predict what is the mean square displacement of this particle is. So here again I am talking about one particle only. In reality there can be other particle and they can also interact, they may actually push and pull, they may attract or repel, okay, and the collective dynamics and the mean square displacement is going to be sensitive to that also, okay. But here we are talking about a free, a single active particle or self-propelling particle. The analytical, this particular problem, this is a very simple problem, this has an analytical solution, okay, because it's a single particle, and this form is basically, this is something you can, it can be solved in a coupled fashion because this is a normal random variate and it's easy to integrate a normal random variate in this way. The moment you add some extra term or when you have some other complicated term, this may not be possible, then you have to resort to numerical approach. But what I can do is, I will show the behavior of a mean square displacement for this particular active particle. This particular problem has an analytical solution, and if you calculate the mean square displacement as a function of time in log scale, you will see 3 different regimes, okay. There is one regime which is called super diffusive with a scale of 1.5, slope of 1.5, then there is a ballistic and then there is a diffusive, okay. So this extra feature here comes in because of the fact that we have added self propulsion here, okay. Without this we would have seen only these 2. Here, this one, because it is purely diffusive motion, right. Remember, for a free diffusion, mean square displacement is 2 dt, right. In log scale, if you plot log of this and log of this, the slope will be 1. Okay, so to summarize, what I was trying to say is that this Langevin equation originally developed for Brownian motion and understanding mean square displacement and mean square velocity can be easily adapted to more realistic situations, okay. And even though this looks very simple, when you look at n particle and when you look at collective dynamics, you see very nice swarming behavior, collective motion, and this is very rich in physics literature, okay, especially in soft matter physics literature. You can look it up. It's a very active field. There are many faculty in IIT Madras working on this field, okay. We also published some papers on this. I'll give some reference for you to go through more complicated models than this, okay. This is something analytically solvable, but many realistic situations that may not be possible, so you have to do numerically. And numerically, when you do, it's not very very difficult. You can use a simple Euler approach to simulate this, yeah. Okay, so with this I'll stop, and there are a few more applications that we will take it in the next class tomorrow.